Well, thank you very much. So I know that the title of my talk is a bit cryptic, but first, let me introduce myself and then I'll explain what it is. So as he said, I'm Lucas, and I also have an alter ego, which is Lucas the Wizard, and that's how you can find me on Twitter. So I'm currently living in London. I maintain a couple open source projects like Chai.js and Sign.js. Who here uses one of them? Cool, nice. Thank you. I've got stickers, by the way, so you can find me around and ask for stickers, and I have Chai stickers for you. And sometimes I also write things on lucasfcosta.com. And some of these things, well, I have some maybe controversial opinions in tech, and when I post them to Hacker News, I don't know if people like them or not. And yes, I do use spaces instead of tabs, but this is not what I'm going to talk about. Okay, so will I talk about birds? Yes, eventually I will. But this talk is actually about Lambda Calculus. So Lambda Calculus doesn't necessarily have to do anything with numbers, right? It has to do with fun. Not this kind of fun, this kind of fun. So Lambda Calculus is what is behind functional programming. So just like Turing machines or is what is behind the object-oriented paradigm, Lambda Calculus is what is behind the functional paradigm, right? So who here trusts me, trusting what I say? Who here trusts Stack Overflow? Okay, I thought actually more people would trust Stack Overflow. So now let me ask you, well, is it useful? Well, I gotta say it is. So differently from knowing about Turing machines, like when you know Turing machines, they don't usually help you a lot when doing object-oriented programming. But when you know Lambda Calculus, it does help you a lot when doing functional programming. And not only because you might understand better how things work, but also because you understand why things are made the way they are. So, well, you actually said you trust more in me than Stack Overflow, but I actually have here an answer from Stack Overflow just to back up my arguments. So if you go to Stack Overflow and you search for how helpful it is to know Lambda Calculus, you see that if you do what us programmers do and go to the first accepted answer, that if you want to program in any functional programming language, it is essential. So let me zoom in a bit here. If you want to program in any functional programming language, it is essential, right? Essential. Got it? Cool. So let's get into the wonderful world of the Lambda. So in Lambda Calculus, everything is an expression, which means that everything evaluates to a value, right? So every single expression you have does return a value. And since Lambda Calculus only has expressions, we'll further subdivide that into 4 other kinds of tokens. So we have identifiers, we have abstractions, we can treat as function definitions, we have application, which we can treat as function invocation, and we have grouping, which is like using parentheses to disambiguate, and I'll show you how that's useful in a bit. So this is a lambda, right? So here we have a meta variable, which is an argument, and everything that comes after the dot is the body of that lambda, of that abstraction, of that function. So when you apply an argument to A, you're just putting 2 expressions side to side, and if you do that to that expression we had, you just get back arg. That's how lambdas work. Easy as that. There's nothing else. There's no pluses, no minuses, none of that, right? And lambdas can only take a single argument. So you can never have A and B, for example. But since lambdas can return other lambdas, if you want to do with 2 arguments, you can then have one function which takes one of them, returns another function which takes the second one, and inside the closure you can do with both. This is also known as currying, as many of you might know. In JavaScript, write it like this. And well, if you see this example, so here you have an add function which takes A and B, and you create another add to function by passing choose. So now when you log add 3, it already has the choose as the A, right? Easy as that. And this is why in Haskell, for example, you define the signatures of functions in this way, right? Because they're curried by default. It's because of Lambda Calculus. So for you to evaluate a lambda expression, you have this syntax. Don't worry, it's going to be fun in a minute. So you have the square brackets, and here we're just replacing x with y. So you just do as if you're evaluating a normal function. You just remove x and you replace it by y. So remove the meta variable, replace the body, right? Here, if you try to replace b by y, you cannot do that because b is not an argument, right? B comes from context, and this will become very important in a moment. So each evaluation step we have in Lambda Calculus is called a beta reduction. And we can only do beta reduction when expressions have beta reduxes, which are when we have applications to them, when we invoke functions, or when they contain an application form, right? One of those application tokens. So when an expression cannot be further evaluated, it is said to be in its beta normal form. So here, in this lambda, if we apply 4 and 2, well, we first replace x by 4, we can go on. If we apply 2 to that result, we will replace y by 2, so we replace the meta variable. Then we can go on, and then we have a result. So these pluses, these numbers, this is all very beautiful, but it's not how Lambda Calculus really works, right? This is just a lie to make it less complex. And I'll show you how it really works in a minute. So parentheses, why do you need parentheses? Because you need to disambiguate expressions. So if you have x, y, and z, and you want to disambiguate, would it be the first option or the second option? Right? What's the order in which you evaluate that? So applications, they're left associative, right? So you group them from left to right, just like when you write proper functional code. So if you do this, you're first applying first, and then the second to the result of that, right? So how do you disambiguate abstractions? Abstractions, they extend as much to the far right as possible. And this is why you need parentheses, right? And since Lambda Calculus is just another way of representing computation, it's just like this pure theoretical model of representing computation, and Lambda Calculus is string complete, we can replace any programming language with Lambda Calculus. And in this talk, I'm going to replace JavaScript with nothing but functions. So now that you know the rules for Lambda Calculus, now that you know the basics of the theory behind it, we can go on and re-implement JavaScript. And I'm not the first one to do this. Tom Stewart has made this before in his amazing talk at Ruby Manor called Programming with Nothing. But I want to take it one step further. So in this talk, I'm going to bring JavaScript. Then I'm going to bring JavaScript with birds. And then I'm going to bring JavaScript and the birds. But then I'll apologize to you. So the rules here, in order for us to rewrite JavaScript, is that we need to rewrite JavaScript with nothing but functions. And just like in Lambda Calculus, all functions must take only one argument, right? But we can have curried functions. So functions can return other functions, and we can apply functions to functions. Lots of fun. So we use assignments also to make things easier to explain, right? So I will assign those functions to values, to variables, so that we can see the names. It's going to be a lot easier, because writing them in line is just pain. So let's get started with JavaScript and replace some booleans. So here, in my terminal, I have this, which will evaluate every time I save this file, right? So you see the results on your left, okay? So for us to replace booleans, let me have a result here, and I'll create a simple ternary. So this just chooses between yes and no. Now I'll start with something very simple, right? So this, when I log my result, if I have true here, it will choose the first one. If I have false, it will choose the second one. So how can we have a function which only takes single arguments and have the same behavior going on, so that we can write code without using any booleans, any pluses, any minuses, or any of that? Right? So for true, I can just have a function which takes A, returns a function which takes B, and returns A, because this is essentially what my ternary is doing, right? It's just taking yes and no and returning the first thing. So I can go on and say that false will do the opposite and return the second element. So if I replace this true, this boolean, with my functional boolean, like this, then I can have the exact same result on your right. If I have a false, it will have the exact same behavior as the boolean false, right? And I'm just using functions. If I want to have some syntax sugar, I can have an if, which is just my identity function, which will just take the boolean and return it, right? So if I want to have like if false, do yes, otherwise no, and just works fine. Now let's do something a bit more tricky and start replacing numbers, right? So first, to replace numbers, this will be a bit more tricky, and this talk is full of philosophical questions, because we must ask ourselves what a number is anyway. Right? So this is true, right? I mean, it's quite obvious. But this is just one of the many ways we have of representing 2. We can represent 2 in binary, in octals, in hexadecimals. We can represent 2 in Romans, many different ways, right? But what numbers mean, like they mean something, right? So this is 2 oranges. So what numbers really mean is repetition, right? As quantities. So there's a difference between how we represent numbers and what they really mean. So we need to dissociate meaning and representation so that we can do that using functions. So how can we represent quantities with functions? Well, we can have function applications, right? So for 0, we can have a function which takes f, returns a function which takes x, and just returns x. If you want 1, we can just apply x to f once. If we have 2, we have f twice, and we can go on and do this many times. And this might seem a bit weird, a bit tricky, but I'll show you how it works in a minute, and I'm sure it's going to make sense, right? Because numbers, they're just conventions between us humans so that we can represent quantities to one another, right? So if I show you the number 2 in decimals, you understand, right? But if I show number 2, I don't know, in binary to someone, they might not understand. And we can create our own systems of representing numbers, right? And we have many weird systems going on. So we can have like 0. So let me implement 0 here. So let's have 0. Let's have 1. So 1, I'll just apply x to f once, and I can go on and have, for example, 2, 3, and here I have f. Did I miss an f? Got so many parentheses, like Lisp. Cool. So now I can see that this is my way of representing numbers. I can have a show function which can just console log something. So I can say that my way of representing numbers is printing something, right? So the more somethings you have, the more quantities you're representing. So I can have a function which is show twice, which repeats show 2 times. So these functions just repeat things, as you're seeing, right? They take f and they repeat f. So when I do this, show twice, and I invoke show twice, I have 2 somethings to the console. I can say this is my way of representing numbers. I can say I can represent numbers using x's, right? The important thing is that I will be able to do operations with these numbers. So I'll be able to compute things. So I'll do a bit of a cheat here, and I'll have a toNum function which will return us the decimal representation of numbers, right? So I'll take a number function. I'll have a counter. And whenever this function I'm passing in is invoked, it will increment my counter by 1. Right? So I can just console log I. So as you're seeing here, since 3 takes f and repeats f 3 times, I'll repeat incrementing my counter 3 times. And now I can come here and do toNum 3, and you see 3. So I just did this so you can see results, right? We don't necessarily need this. This is just going from meaning to representation, okay? So going forward, we can now replace arithmetics, which is what numbers are made for, right? So you can replace numbers, sum, and we can do sum only using functions. This includes numbers, right? We don't need the plus sign anymore. So what is a sum? Well, a sum, when you do 4 plus 2, what you're actually doing is you're just getting 5 and then 6. So you're just repeating the successor of 4 twice. So for sum, if I want to implement sum only with functions, I can have a sum which takes a, takes b, and it's going to repeat the successor function b times for a. So if a is 4 and b is 2, we're going to get the successor once and then twice, and we'll get 6, which is the result. Well, we don't have the successor function, do we? So we need to implement that. So let's go on and implement the successor function. So our successor function initially is just going to take n. Let me put this below my toNum function. So it's just going to take n and return n. And I'll elaborate from there. So we have successor. So let's print the successor of 3. So if I do this, we have 3, right? We're just returning whatever we're passing in. If I want to always return 1, I can copy this definition of 1, and I can put it here, and now I always have 1. So whenever I want to increment a number, I can just wrap it inside f one more time. And I'll start getting 2, now I can get 3, and then so on. However, if I still want to return the same number, I can also do n times f, right? Because f is a function I'm repeating, and here I'm repeating 3 times, and I'm going to pass x, and I'll simply get the same number. So now that I have this number, I can increment it by 1, by wrapping it once more with f, right? And then, if we go on with this, I'll replace lots of things with this, and in the end, we can write code only using functions, right? So we have successor, we have sum, we can go on and we can define 4 as the successor of 3, and we can define, for example, 5 as the sum of 2 and 3. And now if I log them, let me log them here, 4, and now 5, and there we go, we have 4 and 5. So let's go on and represent multiplication. So for me to have multiplication, I need to also take two numbers, a and b. And now, let's say I take f, right? So if I want to return always the second number I pass in, I can just repeat fb times, right? So let's do this. Let's multiply 2 and 3, right? So if I do this, I'm doing b. Oh, let me remove these other things here. I'm always returning 3 because this is the second thing I'm passing in, and here I'm multiplying b by f. If I want to get the first one, a times f. If I want to have both, I can repeat this by wrapping it in a. So now I have 2 times 3, which is 6. So we have multiplication, we can even have exponentiation. So for exponentiation, here, since let's say a repeats something twice, right? So if I have 2, and I want to use 3 as an exponent, and then I can have twice, right? So which is 2 to the 3. So now I can just repeat b a times. And then let's go on and now define 6 as the multiplication of 2 and 3. And let's define 8 as exponentiation, 2 and 3. And we can log that, and you can have 6 and 8, right? There it goes, 6 and 8. So now, for us to replace subtraction, we can follow the same path we've done for addition. So for me to have subtraction, so subtraction is just repeating the predecessor function, right? Sum is repeating the successor, subtraction is repeating the predecessor. But for me to explain that, it's a bit more complicated, because I need to go through wrappers, I need to go through pairs, I need to go through incrementing pairs, and I need to get to the predecessor. We'll do it slowly, we'll get there. So let's start with wrappers. So wrapper is nothing but, I'll say it's like something that puts things into a box, right? So let's here create a wrapper. So our wrapper, it will just take a and f, and then we store something, and we apply that thing to the function we pass in. So it's as if we're putting something to the box and we're opening the box by passing a function, right? So let's do that and have here a wrapper, which will take a and f, and we apply a to f. So we can now have a box, which is a wrapper, for example, Russia. And if we do box console log, we're passing console log to this box, so we're opening it and we're applying Russia to console log, and we get Russia, right? A pair is nothing but a wrapper with two things inside. So we store two values, and then we tell which one we want, or whatever we want to do with both of them, by passing f. And we already have functions which do that. And those functions are true and false, because as you might remember, true and false just choose between the first and the second thing you pass to them. So we can also call them first and second, right? So if I have a pair with a and b, like in this example, and I try to get the first item of my pair, I get a, otherwise I get b, right? So let's do this, and let's have a pair. So a pair, instead of just taking a, also takes b, and then we apply both a and b to that. So we can have a pair with Russia and Brazil, for example, which is where I'm from. So here, if I get, let's copy this and rename them to first and second, because as you see, they just return you the first or second thing you pass to them. So you have a box with first, and if you console log that, you get back Russia. If you console log the second one, you get back Brazil. So this is how you get items from pairs. And now that we have this, we can go on and explain incrementing pairs. Well, this should not actually be called incrementing pairs. This should maybe be called, like, you know, copy the second thing to the first index and increment whatever's in the second, but I don't think that's a good name. So here, if you have 0, 0, the result you get is 0, 1. If you have 1, 2, you get 2, 3. If you have 4 and 5, anyone? 5 and 6, right? Easy. So if you repeat the increment pairs operation 5 times over 0, 0, you get 0, 1, you get 1, 2, then you get 2, 3, 3, 4, 4 and 5. And if you notice that the first item in this pair is actually the predecessor of 5, then this is our predecessor function. Because the predecessor function is nothing but repeating the increment pair operation n times over a pair of 0, 0. So now let's come here and let's go on and implement increment pairs. So my increment pair operation just takes a pair P, and it's going to copy whatever's in the second position of P and put that into another pair. And in the second item, we'll also get a second item of P again. But this time, we're going to increment it by 1. Right? So if I do this, and now I have a pair of 0, 0, which is just a pair with 0, 0 inside, I can then go on and define a result as the result of incrementing pair for 0, 0 ones, and then let's log here my result first and result second. This needs to be to num. Okay? So if I do this, oh, I already defined result here. Let me remove this. Okay, so I get 0, 1. If I repeat it twice, as I've showed you, you will get 1 and 2. So as I repeated it twice, the first item here in this pair, it's 1 less than the number of times I repeated it. So for predecessor, I can go on and say that my predecessor of n will be repeating n times increment pair for 0, 0, and getting the first item out of that, which then allows me to define 7 as the predecessor of 8. So if I now log 7, I get 7. And now I can go on and implement subtraction, because subtraction is just the predecessor of n k times, right? I just repeat the predecessor operation by one of the numbers for another one. So I can have a subtraction function, which is going to take a and b, and it's going to repeat b times the predecessor of a. So this can then, now we can then do something like subtraction 5 and 2. So if I do this, I get back 3. So we already have all these operators working. We don't need pluses, we don't need minuses, we don't need any of that anymore. Well, going on, we can even replace Boolean operators. So now that we have Booleans, we can operate on them, and we can have things like not. So for not, we must think what not must do. Not must just invert whatever Booleans it gets, right? So I can take a Boolean, and I can take a and b, which are the two things I'm going to pass to my Boolean. So if I do this, right, I'm just going to do the same thing as the Boolean is already doing, right? Everyone agrees with that, correct? So let me demonstrate this by having not true. So if I have not true, and I choose between yes and no, then I still get yes, right? Because not here it's just doing the same thing. However, if I want to invert it, so if I want to make true return the second thing instead of the first, I can just invert the order in which I pass the arguments, and all of a sudden it becomes false, right? So if I have not false, it will be true, so you return yes. Okay, so this is how I do not. Now, if I want to do, for example, AND, right? So what is AND? AND needs to return true when the two things I pass to it are true, right? So I have true and true. So let's say I take A and B, which are my two Booleans, right? So if A is true, it will return whatever's here. So if A is true, B still needs to be true. So if I return B and B is true, this function will be returning true. Otherwise, if A is false, well, then there's no way this AND can return true. So I can just return A, because A is already false. Okay? So then for OR just needs to return true when one of the operators are true. If the other is false, there's no problem. So here, let's say I take A and B, right? So if A is true, I can return true straight away, so I can just return A. If A is false, I can then come here and return, if A is true, I'll return A. If A is false, I'll return B, right? Because if b is true, then this boolean, then this end returns true, otherwise returns false. So these are not and or. And I can show them by doing this. So and false returns no, and false and true returns no, and true and true returns yes. If I change this to or, this is yes, this is yes, this is no. Right, so we have operators and not and or working. I can go even further and we can implement comparison. So we can have less or equal than, for example. And well, so I can implement less or equal than, I can implement greater than, I can implement equals, I can implement lesser than, all of that, right? So here, there's an important thing that we need to notice. So let me comment this and show you something. So when you try to do, for example, when you try to get the predecessor of 0, let me change this to now. So when you try to get the predecessor of 0, you get 0, right? We don't have negative numbers. So when you also try to subtract, for example, from 2, 5, you also get 0. So we don't get negative. So if you want to implement less or equal than, we know this, so we can take A, and we can take B, and we can check if the subtraction of A minus B is 0. Because if A is smaller than or equal to B, it will return 0 anyway. What we don't have is 0. So let's go here and implement a 0. So for us to implement a 0, I can now show you another important concept, which is alpha equivalence. So in Lambda Calculus, we say that two functions, they're alpha equivalent when they actually do the same thing, but they just take like different, like they have different names of variables and this kind of stuff. So if you look at false and 0, you see that you can replace the things in 0. So if you want to replace in 0 f by a and x by b, you see that they are actually the same functions, right? It's just the name of the variables that are changing. So they essentially do the same thing. So false and 0, they're the same thing, just in our everyday programming, like in our everyday programming languages. And if you want to rename things, if you want to have a formal notation for it, you can use these curly braces. So here I'm renaming x to a, so I can just go inside the body of the function and the method variable and change its name, right? So here I'm renaming y to b, and I can then just go into the body and just change that. However, if I try to rename z to c, z is not an argument, it's not a method variable, so I cannot do this. Okay? Before I run JavaScript birds, let's go on and now implement is0. So if you take a number a and you consider that 0 being 0 is the same thing as being false, you take a and you need to choose between two things. So if a is 0, it's going to return the second thing, which is true. Right? So if a is 0, we return true, so a0 is true. Otherwise, you can have a function which is a constant, which always returns false. Because if I have true, false, I'll always return this constant, which no matter what's applied to it, returns false. So now, less or equal than, and is0 should be working. Let's try them by getting back our console log. Let me come here and copy that thing I had. Copy this. Let's go back. So we can have is0. And if we use 1, then I get no. If I use 2, I get no. If I use 0, I get yes. Okay, so is0 is working. For less or equal than, I can check if 1 is less or equal than 2, should return yes. 2 and 2 should also return yes. 2 and 2 returns no. Okay, so this is working. I can go on and implement. I will implement this after. I think this is a bit harder. So now let's implement equal. So since we can only get to 0, right, I can take a and b, and I can check if a is less or equal than b, and vice versa, right? Because if both a is smaller or equal than b, and b is smaller or equal than a, that means they're equal, because that's the only way of both returning 0. Otherwise, one of them would be positive, right? So we have equal now. For greater than, well, it basically defined itself already because we take a and b. And if we get the inverse, right, of less or equal then, well then, it means that something is bigger than another thing, right? So if something is neither small or equal, it can only be greater. For lesser than, I can take A and B, and I can check if B is greater than A. So if B is greater than A, it means A is lesser than B, correct? So we can come here and check equals. So we can have 3 and 3. This gives us yes. 3 and 4 gives us yes. Okay, that's wrong. Oh, that's because I didn't invert this. Forgot that. Okay, now it's working. Cool. Live debugging. I can test greater than. So greater than 3 and 4 should give us no. 5 and 4 gives us yes. Cool. Lesser than, this should give us no. This should give us yes. This should give us no. Cool. So we have all that working. Now I can write code with that, right? So I can have a function, fun, which takes A and B. Let's do some crazy stuff now. So here, if A is bigger than B, right? I can do A times 2 plus B. Else, if A, B is bigger than A, I can do B minus A. Otherwise, I can do, I don't know, math.pol B and A. Cool. Now let's try this. And let's invoke it so that we fall into every branch and all branches, and then I'll replace it all with functions. So here, let's do console log. For us to fall in the first branch, we can have A bigger than B, so we can have 4 and 2. We can go on, and we can have B bigger than A, so we can have, I don't know, 1 and 5 and 6. Yeah, okay, I think that's good. And if they're equal, we can have, I don't know, 3 and 3. Sounds good. So if we do this, we get 10, 5, and 27. And now, since Lambda Calculus is string complete and I have already defined all this, I can replace all these with functions, and I can have code using only functions. And this is why Lambda Calculus works, right? So it just chooses between things, and you can express any program that was ever written or that will ever be written, right? With just those 4 tokens, you can write all programs in the world. So here, let's take A and B. Let's make them curried, as in Lambda Calculus. And now let's make this look like Lisp. So we have if, and now we can have if A is greater than B. We're going to do whatever's inside here. So let's do this. And if that's true, let's multiply A by 2 and sum that to B. So here I'm just rewriting this using the functions I have defined earlier. So otherwise, I'll fall into the second condition. So I can just have another if, which will check if B is greater than A. And then, if that's true, I'm going to fall in this condition, which just subtracts B and A. Otherwise, I'll fall into my else, which will finally do exponentiation. And then we're going to have B and A. Okay? If I do this, I can now do this and this. So we have replaced everything here only with functions. Now I can come here also and replace all the things with my functions. Can I replace this with 3 with 3? 3, 3, yes. 2. And then here we have 6. We're going to do this, this, this. Let's make this to num. Come here, invoke this the correct way, because it's curried. And we have the exact same result. So we can have, thank you. So you can write all programs using only functions, right? Everything that you have in JavaScript, you can implement it like this. Okay? And now, let's go on and run JavaScript with birds, right? So why birds? Well, birds, they're just functions that don't have any free variables. If you might remember when we were doing replacing and renaming, there were some variables we couldn't replace or rename because they were not arguments, right? So in the first example on with context, you see that A is bound to a variable, so it takes that as a variable, as an argument, and B is free, so B comes from somewhere else, comes from the context. In my combinator, both A and B are bound, so both A and B are arguments. But why do they have bird names? Well, they have, oh, I forgot this slide, so let me do a quick quiz. So here I have one, so I have X and X. Is this a combinator? Is it a combinator? Yes, it is, because X is bound, right? So X is the only thing I'm using in the body, and X is bound to an argument. Is this a combinator? Anyone? Nope. Cool. Because Y is not bound to an argument. Here, is this a combinator? No. Cool. You're good at it. Here, is this a combinator? Nice. So they have bird names because of this book by a guy called Raymond Mullion. So in this book, Raymond goes on to explain combinatory logic by using different combinators. So he gives you like a few axioms, and so he treats combinators as birds that hear the name of other birds and sing something and give you an answer, right? So he explains combinatory logic in that way, right? And this is how, this is what it has to do with math, right? Because combinatory logic is a notation to eliminate the need for quantified variables in mathematical logic, right? We don't need to have those number symbols, right? So in it, he calls some of the combinators, some of the ones I already showed you, with names of birds. So the identity function, he just calls it the i.bird, the e.bird. The kestrel is just true, right? It just takes A and B and returns A. Here, the kite just takes A and B and returns B, which is just like false. The cardinal, just inverse things, is the same as the not combinator. The virgule is nothing but the pairing combinator, right? So we just take A and B, and we put that into a box, and we open the box with F. The bluebird, which is the name of the stock, which is, by the way, a reference to Bukowski's poem, and plays well with Raymond's book, is because the bluebird is function composition, and this is what like many people talk about when they talk about functional programming, right? And if you look closely, you see that function composition is nothing but multiplication. The thrush is a wrapper. This is a small, purely functional data structure, by the way, as you can see. The stalling is a bit more complicated, but the stalling just takes f, g, and x, applies x to g, and then applies that to the result of f of x, right? It's complicated, but we'll get there. And also, one last combinator. Have you heard of this one? Well, it is a combinator, and this is why Y-combinator has this name. So the Y-combinator is a combinator that allows you to do recursion. So you can do recursion without using any names. You can have recursion without having to assign something to, like assign a function to a name and then call that name again inside of the very same function. Right, so this is how you can have recursion in a language that doesn't allow you to have explicit recursion, right? So if you go into the website, in their FAQ, they have one of the answers is why did they choose the name Y-combinator? Well, it's because the Y-combinator is one of the coolest ideas in computer science, and is also a metaphor for what we do. So it's a program that runs programs. We're a company that helps start companies, just like the Y-combinator, which is recursion. And well, I could have an entire talk explaining this. I think Jim Wirish has an excellent talk explaining this. I think he takes like half an hour, 40 minutes. Unfortunately, I don't have time for that, and I would need lots of visual resources and stuff. But I have a blog post which explains it, so you can just go to lucasfcost.com and read it. If you want to translate it to Russian, that would be also an honor for me. So now going forward, we can replace functions now with these birds. So the successor function, if you look closely at the bluebird and the successor function, since the bluebird just does composition, and here we're just composing two functions, which are f and n of f. We can now remove x, right? And just take nf, because that's what we're composing with the bluebird. And going forward, you see that the stalling has the exact same form, right? Takes f, g, and x, and applies g of x to f of x. So you can now replace n and f with the starling. So the successor is nothing but the starling of the bluebird. And we could do this for all of our functions. So for addition, we have n times the successor for k, for example, right? And we have just seen that the successor function is the starling of the bluebird. So let's put it here. And then you see that here, what we're doing is we're invoking n of s and b with k. So we can have the thrush and have the k there, right? And we can even have the cardinal of the thrush of all that, right? So here, if I go on and I get those birds, let's get those birds from here. Already have them. So I can go on and put those birds here and start replacing things. So I can replace my if with the ibis or the idiot bird. I can replace true with the kestrel. I can replace false with the kite. I can even go on and replace the sum and the successor with these. So where sum and successor? They're here. So I'm replacing them only with birds. I can go on and replace multiplication. So let's replace multiplication with the bluebird. And if I save this, I still get the same results. So I could go on and replace everything with birds, but I don't think that would be very interesting. I think that would be actually very exhausting. So now I can go further and bring JavaScript and the birds. Because, well, you don't need all of them. So just like you don't need any pluses, any minuses, or any of that, and just like you don't need all those different functions, you just need combinators, well, you can replace all the combinators only with s and k. So just the starling, right, and the kestrel are enough for you to have Turing completeness. So as I've said, you can write any programs that were ever written or that will ever be written only using those two combinators. And some people call it SK calculus, other people call it SKI calculus, just because it's more convenient to have I. I mean, it's already very convenient, right? But in fact, I can just be defined using S and K, which are the only two you need. And there are many different combinator bases, is what they call it, that you can use to have Turing completeness. This is the smallest one. So for kite, you can derive kite this way, only use S and K. But since SKK is just I, if we're using SKI, we can do this. It's so beautiful how like they name things after the definition with S and K. So cool. The bluebird is this, and well, C, the cardinal, is just like this very simple thing. So we can now just go into our production code, start replacing everything with S and K. It's going to be amazing, great performance, just functionals. Now, you'll be the most functional people that the Earth has ever seen. And well, I've just introduced a few of the birds, right? They have so many birds, and you can find off them at this link. The slides will be online after this talk, by the way. And here, they have the definition of them and the names of all birds. So if you want, you can go there. You can see all those birds. Some of them have very strange names, like the double mockingbird and the once removed something. It's really cool. But well, what does this mean? Well, as I've said, if you can replace all code by functions, if you can replace all functions by combinators, and if you can replace all combinators by S and K, this means that you can replace all code by S and K. And there's some people that have done tools that do this, just in case you want to play with them, just in case you want to do this in production. Well, why did I do this? Well, I did this because I think this is a great way to get started into also like reading papers, because when I started out, I found that actually reading papers about functional programming is really complicated. Has anyone here gone through this experience? Okay, so yeah, like if you read papers like about, for example, recursion schemes, there's much of the terminology there that's hard to get, right? So once you understand the basics of Lambda Calculus, which I believe sometimes people make it way too complicated for no reason, like it's a really simple thing, it's going to be a lot easier for you to read papers about subjects just like recursion, like about computability theory, like even about functional programming, and you understand why things are made the way they are. About maths, trademark, combinatorial logic, which has a lot to do with the book I've just talked about, compiler theory, and even wanting to frame ghetto pictures to hang in a room because he's an awesome guy, and you'll be his biggest fan once you start reading about him. In the end of this talk, I always like to put a list of the best places to start as well. So I definitely think you should watch and read all of these. So there's the Tom Stewart talk I've mentioned, in which he does one of the parts of my talk in Ruby. So he has a bit of a different take. He's amazing. You should definitely watch that. There are his slides. There's the list of notorious combinators I've showed you. There's a talk by a guy called Gabriel Lebeck, which is amazing, which he goes into much more detail about combinators. There's the book called To Mock a Mockingbird. There's Tom's book, Understanding Computation. And here, this is, by the way, a really interesting one. It's the lectures by a guy called Adam Juppé in the Arizona State University, in which he goes on explaining all the formalities and even the history of Lambda Calculus. So you should definitely read that. I think Computer File has some pretty cool videos as well. There's plenty of material online. But I think instead of just starting by reading papers, it's good for you to go on and read these first. And also, you should definitely stay for the next talk, I think in this track, where the next guy is going to talk about type theory, type systems. Well done, nice. So are you the next one? Okay, good, so you should watch him. Well, thank you very much. I hope you have liked it. You can, yeah, thank you.